Hello. Good afternoon, everyone. So welcome to our tutorial, Deep Natural Language Processing for Search and Recommender Systems. So I'm Bolong. This tutorial is joint work with my colleagues, Wei Wei, you will see later, Huiji, Jun, and Liang, Bichuan, and Deepak. Yeah. So our tutorial will have the 4 parts. The first part, the introduction. We're going to do the general introduction about NLP and the search recommender system. And the second part, we'll do an overview about deep learning technologies for the NLP. And the third part will present the application of deep NLP in the search and recommender system. And the last part, we will present the real-world example from our linking applications. I will start with the first part and do the second part. Our colleague Jun and Wei Wei will do the third part, and my colleague Huiji and Liang will do the last part. So as we all know, search and recommendation now everywhere in daily life. When you try to find the information you need from the internet, it could be news, job, and food, all those kind of information. When you do this, they provided by the either search or recommender system. When you explicitly provide the queries, and the search system will based on your query to provide the information you're looking for. If you don't provide the query, but the recommender system can based on your profile, right? Your historical behavior, right? To understand your interest implicitly, still can find the information you are looking for. So can you see a simple example to see how search and recommender system help us to find the information we're looking for? I guess almost everyone search this query, KDD 2019. Then after you register this conference, right, and you will do your travel planning, you will find the hotels in Anchorage or book the flights. After you have all those travel planning ready, you arrive at Anchorage. You may find the food in this area, like king crabs. That's what I did yesterday. So then you will think about, besides the conference, you want to do some sightseeing, find the interest places to sightseeing. Then you come to the KDD, first day, our tutorial, and come to our tutorial. You may find my presentation kind of boring, right? You may not search the attraction in Anchorage. Someone maybe are doing that. Okay. So, but later you may find our tutorial actually interesting. You learn something, and you want to learn more. So you may find a book about deep NLP in search recommender system on the Amazon. By the way, there's no such book. You still have a chance to write one. So that's about learning, right? You will meet a lot of people at the KDD. Then you may want to search them at LinkedIn to get connected, make more friends, make more connections. And our recommendation system will also recommend more people for connected. That's people you. And the right hand, encoder, decoder, right? Generate new sequence or sequence combination. It's generate a new sequence of text information. It's NLG, natural language generation. And in the middle, it's a matching, right? You have to understand the generation. You really want to match the information. Matching the information, you want to provide user to user intention. So these 5 are going to be in the sequential model. But for all those modeling, not typical implementation, the input is going to be the word identity for all those tasks. So there are also the average focus on how to learn the word identity for the words from the sequence. That's called representation learning. Basically, try to get the good data representation for the NLP data. Then you can do other tasks more efficiently. So we're going to separate this one to the representation learning. Okay, so in summary, we can classify this deep learning into 2 big categories. One is to do the sequential modeling. on the semantic text. Another one just focus on representation learning for data processing. So in the following, we're gonna first talk about the sequential modeling for semantic context. So for sequential modeling, the input is sequential words. The sequential words on the top, we do the sequential modeling. And then we get a sequence encoding. We can also call it feature embedding, which actually captures essential semantic information for this sequence. Then you continue to finish the top tasks like classification, segment analysis, tagging. Now let's take a look at the state-of-the-art algorithms to do the sequential modeling. To explain this, I'll use a toy example. This simple sentence: I'm an NLP engineer. So we try to first get the encoding for this sentence, right? The words in the sentence. And the second is we do the encoding for the individual word, which we call the unique graph. Typically we do this with deep learning algorithms. We use the MLP, multi-layer perceptron, to do this. However, you want to do the more context, right? Like a bigraph or trigraph, which normally we use the convolutional neural network, which capture local context, basically the window around that word, the current word. However, if you look at the sentence, right? If sentence is very long, this n graph is going to be a challenge, right? You need to have all the information from a sequence. How are you going to assume the sequence, right? All the information passing along the sequence. To capture this information, which is accumulated context. Right? For example, this engineer, his information and got also affected by the first word I. How, if the sentence is very long, how we will also capture this accumulated context, which typically we use R1, right? Currency neural network. When we have this MLP engineer in application, for example, translation, right? And also from this, we put a source sequence into a target sequence. For example, we translate this English sentence into the French. Right? Then you need also the translate this context to your target sequence. So this is about the context translation, which is sequence to sequence model. You need to capture context in the target sequence. Then you can really make sure you get the good generation of the target sequence. So when you do this sequence to sequence model, the one context way you want to capture maybe also from the source sequence. When you do this translation, you can see the one word in the French, it can also have context from multiple words from the source sequence in English. And those different words give different context, maybe have different stress. Yeah. So that's where you want to have the stranded context stranding, right? The different context from sources with different stress, which you can use attention model to do those different weights from context from source sequence. That's where attention model can use. And so far you can see we have the context simulation just one direction, right? But to capture more context, you want both direction. And that means you want context more global, right? From different direction, you can understand the current world. Which how we have used the transform model to capture global context. Even with transform model, we still have a challenge. That's called the exposure bias. We think about the sequence model. When you do the training, the word generated actually current word is generated based on the actually previous ground truth. Because when you do training, you have the ground truth. However, when you do testing, you don't have the ground truth. So your current word actually generated based on the previous prediction. You see there's a discrepancy between the training and testing. We're going to cause some issues. To solve this, the latest algorithm we can use GAP, generative adversarial network, to do the content consistency. So this gave the principle how you list different solve different LP tasks, different challenges. Let's look at a little bit more details about different algorithms. First, the multi-layer perceptron, like we mentioned, which is a simple neural network structure to capture uniform context. You give the input with a sentence, you do different hidden layers, and output give the embeddings, and on the top you can do tasks. It's pretty intuitive. And if you want to capture more local context, like algorithm, we use the CNN convolutional neural network. So C works like this. You first have this word embedding matrix for each word. And for the next layer, you use the different region and different filters to capture local context. Different region means different size of the window, right? To capture the context. And different filters will different ways to capture different semantic meaning. After this, you have all those embeddings. You want to concatenate together. Then you do the next pooling, basically to get the most important information from those output. And put together will be your high-level representation for this word in the sentence. And on the top, then you can do the NLP tasks and classification. Like we mentioned, right, if you want to really capture accumulated context along this sequence, you need an RNN, right? Recurrence neural network. The basic idea is for each word you have a hidden state. So this hidden state depend on not only on the current word, also depend on the previous hidden state. So you have chain of the hidden states. By this way, you can accumulate the context information following the sequence. But there's a challenge, right? If you accumulate all the way along the sequence, you're gonna get a lot of information, right? Too much information means get too much noise, right? Like a human being, if you have too much information in your memory, right, it's difficult to handle. A human being will use the way to handle it, just forget something, right? So that's why we come to here. You have RSTM. They have 3 gates, right? Input gate, output, and forget gate. So basically, the intuition here is you try to accumulate the most important information along the sequence, but use forget gate also control some information you want to throw away, which is not that important. So you can capture essential information. GRU is a simple way of the RSTM, only have 2 gates. So RN can capture accumulated context information. Now we have a sequence model, right? In generative new sequence. You have, for the sequence model, you have an encoder, which get the input and generate the high-level representation for the input. And based on that, the decoder will generate a new sequence. So that's you can also pass the context translation to the new sequence. That's sequence model. Like I said before, right? For the sequence model, if you also want to capture context from the source sequence,
Не, sono dei scaboli neki šlo.
Proba malo porukati tom kablu. Mislim da će se kaj promakne.
Ok, program.
Hoću da ga vam pogledam.
Hidden state from decoder also depend on the hidden state of encoder, and with attention weights, because the effect of those hidden states are going to be different, so we are set different weights. So this is called the attention model. You can stress a different context from source sequence. And as I mentioned before, right? You also want to capture global details, not just follow the sequence, right? Not just one direction. By doing this, we can use transform model.
Moja treba kabel zanimati. Zanimljivo sam.
Not just follow sequence. It's just global, right? Everywhere can be your context. So doing this way, for each word in the sequence, we have 3 transformers, right? Q, K, V, which is that for priority, key, and value, right? And this transform matrix is going to map the word into the semantic space, right? And into this new space, you can calculate the similarity between this current word and all the other words based on the Q, K, V. And use the similarity as the weight. You can do the weighted sum to get a new representation. So by doing this, we can see if you are considering the similarity between this one and also all other ones, we get a global context. And also, of course, we can use multiple sets of transform, which called the multi-head transform model. So this is to capture global context. But with the transform model, like we said, there's a challenge about the exposure bias, right? When you do the training and testing, there's discrepancy. And again, right, can help to solve this issue. When you use again to the sequence model, right? So you still have the sequence model, which is in the generator. But you also have another model called the discriminator. So for the generator, it's different from the simple sequence model. You can see from here, right? When you do the decoder, the word that you generate, it's not just based on the ground truth. It's also based on the previous prediction. First to do that. Of course, when we do this, you will say, oh, that one you're gonna have the error propagation, right? Because each time you generate the new thing based on the old prediction, if you got an error, you're gonna accumulate. And here comes the discriminator, gonna help solve that. Right? When you generate this prediction, you're gonna feed into discriminator. Discriminator have the ground truth. They will find the descriptor or error between your prediction and the ground truth, and feed back, propagate to the generator to help update the model. Came to this situation, they can force the generator, the system to improve. At the same time, because based on the previous generation, you don't have that exposure bias. So this is kind of how we solve the context consistent issue. Okay. So we can see all those errors about the sequential modeling touch different tasks. So next I'm talking about the representation learning. Only focus on how we learn effective word embedding or higher representation for the data. So for the representation learning for data processing, again, the input is still sequence of words. But our purpose now is doing the representation learning. So we can get the word representation. We can also provide embeddings. Then further we can, based on this embedding, do the individual tasks. So the typical way to do the representation learning is a word to vector. There's two ways you can do word to vector. One is CPUW, right? It's context based on vector words. So basically here is use all the neighborhood context words to learn the embedding for the current word. On the other way around, you can do the skip graph. Use current word to learn embedding for your neighborhood. The context words is word to vector. So word to vector is static word embedding. In a sense, give a corpus, right? No matter where the word it is, right? So we can have the same embedding for this word. So it's static. But we know embedding also based on the context. That's why here we come to the contextual word embedding. First model, Elmo, right? Standing for embedding from the language model. So for Elmo, you can see we have two directions here: the left side, the right direction, capture both contextual. And also have two layer STM, which can capture sentence and information semantic meaning too. And put together, and on the top we get the word embedding, which has contextual information. So it's used bidirectional STM. And another model we use neural contextual embedding, GPT. It's generative preacher model. This one uses transformer model, like I mentioned before. They have three transform matrices, but I only use transformation model in the one direction, forward in the one direction. So it's a one direction transformer, try to capture the context. And intuitively, you can do the bidirectional transform. Right? You use transform in both directions. The one direction can do the prediction naturally, right? Follow sequence. Another way you can mask some words and do another direction. This actually the famous bird, right? The bird actually do the bidirectional transform. Then you can do the multitask learning. It has been proven very well in multiple NLP tasks. This bird is the bidirectional transform. However, in BERT, there's assumption. When you max the words, you actually throw independence between these maxed words, which is not true, right? So to address this issue, recently this new technology XNet, right, come out, which can also modify the correlation among the masked words. So the bidirectional also another correlation among the mask tokens. Right? So this gave the further improvement for all kinds of NLP tasks. This is just published this year. It's pretty new. If you look at Alma, GPT, and BERT, and XNet, right, it's all pre-trained NLP model. Right? This has big benefits because we know when we do the NLP task, normally you have huge amount of data. You need to spend a lot of efforts to processing data, finishing training, a lot of computation, right? Get a model. But with pre-trained model, right, you can save a lot of efforts for the specific application. You can get a lot of huge amount of data, right? Train a big model, which is a pre-trained model. And when you do the special application, you can just on the top of this base model do the fine-tuning, which is much more efficient. So, this pre-trained model was helping NLP task level. So in the summary, we can see for the sequential model, we handle 5 tasks, and we have this different type of the algorithms from NLP, CNN, RN, sequence, attention model, transfer model, and again to handle the different challenges from the sequential model tasks. Another side. We also have the algorithm focus on just model representation, which is a critical part for all the NLP tasks. And we also have all those algorithms, word-to-vector algorithms, GPT, BERT, and XNet to learn the representation. And we can have a pre-trained model to efficiently adjust to different domains NLP applications. So this covers all those state-of-the-art technology, natural language processing. This had all the reference we used for this part. Feel free to take a look after that. By the way, we're uploading a slide on the website. I'm not sure it's finished or not. Not yet, but you can check if you want to also take a look at the slides. So in the summary for the first part, so the NLP is critical for the search engine system. And we have all these different category NLP algorithms to handle different challenges, especially the context information for the different tasks. And now, next part, our colleague will talk about how we apply the NLP in the search engine system. I'm gonna hand it to my colleague.
Come slide.
This is a huge crowd. So when I signed up for this tutorial, I told maybe 20 people sitting in the audience. This obviously is a huge underestimate. This is good. So I hope this will be useful. The tutorial will be worth of your time. By the way, my name is Chunxi and from LinkedIn. So this unit, I'm going to talk about the deep NLP in search or recommender systems. Mostly this part I'll be talking about language understanding. So this is the outline of this section. So I will be covering the language understanding part. It's a highlight here, and also part of the document retrieval and ranking. So let's start with sorry, let's go back. So Language understanding. So Bob talked a lot about the NLP technologies. Those are great. But at the end of the day, you want to use it in a practical system, right? So one of the things we want to do with search and recommendation system is, we need to understand. So language, right? How do machines understand the human language? That's very important component. Understanding our understandings are at different levels. So you can talk about one level understanding. For example, entity tagging, right? That's a one level prediction, and entity disambiguation. And also, maybe we build upon that. We talk about intention classification. Usually, it's a sentence level, and also we talk about sentiment analysis and opinion mining, which is even higher level, sentence level, or even document level. So that's how we're going to talk about this unit. So let's go to entity tagging first. So we're going to talk about what problem we're trying to solve, and what are the traditional statistical methods. So I want to go over the traditional methods, and also to introduce the deep learning models. Then talk about what kind of training data set we have, and how do we evaluate it. Entity tagging, the problem statement is, so first of all, what is entity? Entity is nothing but just words or phrases which clearly identifies one items from a set of other items that have similar attributes. So basically, if you speak English, the words with capitals usually are entities. Capital letters, people names, street names, company names. These are the entities. Entity tagging. Sometimes in the literature, if you read a lot of papers, usually people call it a named entity recognition (NER). This is the process of locating and classifying the named entity in text into a predefined entity categories. So basically, it's a classification problem. So let's say I have a sentence like this. Washington D.C. was named after George Washington. And immediately recognize there's a location. Sometimes we call it geolocation or geo. Then there's a person, right? George Washington. So at LinkedIn, actually, we make finer categories. So like first name, last name. But basically that's the name. So the problem is to identify these entities. So why do we need to do that? So from a search system point of view, mainly if you want to search for something, these entities contains a lot of information, and you can speed up your search by just looking at all these entities, and they pretty much capture most of the ideas. And also, if you can match entities and the tags, then it will increase the search precision. And also quality, you can use this for ranking, and hopefully it will give you better quality, search quality. So let's take a look at the traditional statistical models. So a lot of people here had this maybe speech background or signal processing background. So the very first model we talk about is a hidden Markov model. So it is a generative model. So the other two models we're going to talk about are the maximum entropy Markov model and semi-Markov conditional random field. So the latter two are discriminative model. So the difference between the generative model and discriminative model is that the first model the former actually it generates, right? You give the model, it can generate a sentence for you. The second one actually it does not generate a sentence, but it tell you which part is what. So it's like a classification problem. So let's go over the hidden Markov. In the hidden Markov, so the problem we're trying to solve is you see a list of words, right? Basically, it's a sentence, and you try to figure out the individual tags for the tags for individual words, or maybe phrases in this case. The hidden Markov goes like this. You start with some dummy state. You always start with some T0 state. then you go to, you figure out what's the transition property to next state, and from that state you generate a word. So there's you can think of there is let me just try. So there is a state transition, and also there is emission, right? This is emitted word basically. So there's emission property. So you keep going, it's T2 and W2 and all the way there to the end. So the reason I said this is the generative model because it's trying to model the joint property. Give the joint between the tags and the words. Instead of what we really need is just given the word what our tags are. So this actually it's overkill to some extent, but it's proved to be very simple and very useful. So I have a question here. So basically, sorry. So the idea is right. You have a state that will generate a word, and you give a previous state. What's the probability of getting a next state? So maximum entropy Markov model is slightly different. So in that case, you not only look at the state, but you also look at the word itself. So in this case, you start with a dummy state. Then you observe the first word and try to predict what is the next state, right? And then you do the similar things, and eventually find complete the whole sentence. So again, it's slightly different here. You're given the state and you're given the word and you try to predict the current state. What's different in the expression here is you can include the features. The features usually it's very important for machine learning because in the previous state, previous model, you actually do not have features. You basically just a state and a word. That's it. Right, so that's why this model is more powerful. So conditional random field is an extension of a previous model. So in that case, you see, you have a state, the current state, the previous state, and you see the whole sentence, right? Not just the words, the current word, but actually the whole sequence. And you can use that to create your features, and you predict the first tag, second tag, and so on and so forth. So again, this formula looks like the previous one. The difference is in this the numeric denominator. So the denominator actually is it's a normalization factor. It normalizes over the sequence, all the sequence, not just the one state. So that's the difference. So it is possible that you can extend that to multiple words. So a lot of times, like George Washington, it's a phrase, right? The whole phrase is a name. So if you have a name here, and this is George Washington, you should combine it. So a simple Markov conditional random field basically you include a length to the model, so you can have a phrase. So this is a summary of the traditional models. Hidden Markov is really simple. It's simple to train, but it's difficult to include features. Then the maximum entropy Markov model, it's easy to include features, but because it is marginalized over a state, so it has like a label bias problem. So I guess it prefers states with a low number of transitions. Conditional random field, it does not suffer from the label bias problem, and it's easy to include features. So the last one actually is the one usually shows the best performance, and this is what usually we use in production. So that was the traditional method. So I want to go through the deep learning models. So deep learning models usually it has 3 layers. So there's input layer. Basically, you get all the word embeddings and other stuff, and you feed it to a next layer, the context layer, Then you decode it. You figure out what the text should be. So input layers, Bo already mentioned, so the model itself does not process English words. So you have to, it's a mathematical model, so it has to be mapped to some mathematical, numbers or vectors. So in this case, word, a word can be mapped to word embedding, right? So that's by, so each word can be mapped to an embedding. But of course, you can do a little bit more than that. You can use, if you want to be, be more complex, you can work on the letters. You can work on the letters, and you can look at the character embedding. So the reason for that is, first of all, your vocabulary size is much smaller. You have 26 letters, including all the punctuations and all the other symbols. So it's much smaller than the word vocabulary. And it handles out vocabulary word. So sometimes you have no matter how big the vocabulary in the previous model, vocabulary in the word embedding, no matter how big your vocabulary size is, there are always out of vocabulary word which you cannot handle, and usually people just put unknown there and as a catch-all embedding. So that actually is not very good. But with characters, you actually can capture those prefix. You can understand the prefix or suffix and all the other things. And you actually, even though the word you never seen this word before, but you can capture the meaning. So that's the benefit of this. Of course, there's a penalty. We need to pay a penalty for this. But characters usually become much longer. The chain is much longer and very slow. So you can actually combine them. You can do a character level first. Then you do then you combine with the word level and content and you feed it to the upper layer. So that actually gives you the most benefits. So in summary, input layer usually have a word. You use the CNN, RN to become the word embedding, character embedding, and you can also include external features like from lexicons, from other source. So now let's talk about once you get the embeddings, right? What are you going to do with it? Can you just do a decoder right away? And usually people do not do that. Usually you want to put another layer on top of that just because the embedding itself. A lot of times just to talk about it, it has only meaning about the word itself, right? A lot of times the context is very important. So for example, this is an example of the CNN, so the convolutional neural networks. So in this particular picture, we have next three, right? 3 words. Each author here look at 3 words. And you have a sliding window. So in that case, you kind of have the context. What's the words before you and what's the word after you. In that case, you have this context information. That's why it's called a context layer. And of course, you can do a little bit more. You can use RNN. In this case, we actually use the bidirectional RNN. So you can look forward, look backward. Do both direction. Now, once you process the neighborhood context information, so what are you going to do with it? So usually it's a classification problem, right? You have all these. So this is an example. Michael Jeffrey Jordan. So I suppose this is the person's name, and you start with. This is probably the first name, middle name, and last name. So you can put you had a context in the vector here, and you put just put a context layer. Then on top of that, you predict and a softmax. You use softmax to predict what type this should be. So there's a BPR basically it's the beginning of the person name, beginning of person in the middle of the inside of person, and also the end of the person. So you could do CIF as well. So the CIF basically is a sequential tagging algorithm. So you will tag that for you. And also you can do RNN on top of that. So you remember RNN also a sequence model. You can get this encoded, and then you can have this feed tag back to the model. And Bo also mentioned that there are a lot of very powerful pre-trained models. right? The model is trained on the unsupervised corpus. Then you can also you can do a fine tuning later. Use a very little training data to to fine tune this to basically figure out what the tags are. So this is the bird, this is the GPT, this is the ML. They are very powerful actually. They usually provide the state of the art performance. So how do we evaluate? So for people familiar with information retrieval, usually this is very straightforward. If you look at the position call, and if you want to combine them, it's F1. So there are lots of training data set are available. You can if you can look for them. Those they are different. They are different level of tabs. This one you start with 7 and 4. There's just O and L. The 3 is usually we usually use. And of course when you go to like special domain, for medical. I mean, it has a 700 tab. So it really depends on the domain, but the algorithm itself is more or less the same. So these are performance, and I think we're going to skip because time is very limited. So next thing I want to talk about is entity disambiguation. So again, I will talk about what this problem is, why we're doing it, what are the challenges. And so we'll talk about in reality how people actually design this thing. What's the system architecture, and how do we evaluate it? So for people familiar with this term, usually it's also called entity linking in the literature. So the idea is, previously we know George Washington is a person, and let's say you have a Wikipedia database where you have a large base and you want to find out, what exactly, that name refers to, right? So basically, you want to resolve the mentions to entities. So mentions are usually named entities, and the large base can be freebase and Wikipedia. So here's an example. So let's say you have a word Java, right? So look at the first sentence, we immediately know that this is this is the animal. But Java can be a car as well. So the second sentence, most likely the Java means a car. So the reason we wanted to do entity linking, entity ambiguation is it's very ambiguous a lot of times in the term. So if you look at if you're looking for Michael Jordan, right? So a lot of people, the first thing that came to my mind is basketball player, right? The basketball player. But of course, we have tons of them, at least 10 Michael Jordans. And when I was looking for Michael Jordan a couple of days ago, I was looking for actually the professor at Berkeley, because I was interested in a lot of his paper. So it's very important that when you search for something, when people recommend something, you need to understand, which entity you're recommending, or maybe which entity you're searching for. So what are the challenges? First of all, there's name variation. New York, Big Apple, they're the same thing, but people call it different. And I just showed you that Michael Jordan, you have 10 Michael Jordans. Which one do you want? So basically, a word can be in this case, Beijing can be a city, can be a Chinese government. So which entity you really referring to? And sometimes the entity may not be in the large base, and you have to figure that out. You cannot just map to an arbitrary entity. And also, sometimes the information evolves. And for example, the company name. At LinkedIn, we do a lot of company name linking and classification. And we need to keep up with all the new company names. So here's a system architecture. So usually, you take a document. You need to go through you firstly tag all the entities. You find the entities and you try to generate what are the candidates for this entity. Then you select them and you output the result. And you need basically a large base for this. So how do you generate a list of entities for a mention, right? So someone has said Michael Jordan. So how do you get this list? So usually, it's dictionary based. A lot of people use a dictionary based method. You go to entity page. You go to redirect. If you have if you use a Wikipedia, you can have a redirect pages. Basically, that means that this page is related to that one. And also, sometimes you have a disambiguation page. This page basically tell you all the possible candidates, right? So you can also do like surface expansion, and you can do a search engine. There are different ways to generate. So generating them is relatively simple, but the problem is, I give a sentence. Can pinpoint me to the exactly right the entity in the knowledge base? So there are two ways to do it, at least two ways to do it. One way is graph-based. So, think about it, this is knowledge base. It basically is a knowledge graph, right? You have connections, you have nodes, you have connections. Let's say, in this particular example, you have all the red nodes are mentions. Basically, the entities you find in the sentence, and also there are entities from the knowledge base, and you connect them. And the idea is, you can connect them and with different weights. So you want to find a subgraph of this whole thing, and with some conditions, right? Subject to some conditions. For example, one mention has to map to one entity. You cannot map to entities, and also, it has to contain, the subgraph has to contain all dimensions. And also there's some kind of optimality, right? You want to find the optimal. You can just randomly choose one. So here's an example. On the left is a paragraph, right? It's a very short paragraph. They basically, there are a few, they highlight a few, entities. The Kashmir, Page plant, Gibson. So it turns out, in this case, Kashmir, you have two options. Page, there are three options. So you figure out which one actually give you the best performance. So since we are talking about NLP, I want to focus more on the text-based model. So that was previously was a graph-based. So now let's think about the text-based. So basically, what you want to do is you want to find the entities, a similarity between the entity dimensions. So in this example, right, computational intelligence by Michael Jordan and Stuart Russell from UC Berkeley. So if I want to ask what Michael Jordan, who is this Michael Jordan, right? So let's say I have two options. One is if you go to Wikipedia /Michael Jordan and /Michael I Jordan. So it turns out the first one is the basketball player. The other one is the professor at Berkeley. And I think most people will pick the professor mainly because in the context. That's what it means. So context is very important. So according to the context, the model can be, you can have 4 different levels of models, right? So you can, a direct model, basically, you just look at the mention itself. So you want a Michael Jordan, so I just look at Michael Jordan and I say, hey, what's the one that most high, give you the, which one has the highest probability? Of course, the basketball players, because a player, he's so popular that everybody knows it. But that does not consider the context. And so if you go down the list a little bit, you have local context. So you can look at the left and right. If you look at the computer intelligence, and you can look at the Stuart Russell, then you know that this cannot be a basketball player. And also this has if you go down one more step, you see it could be coherence model, right? So basically, the mentions themselves, they should talk to each other. So if Michael Jordan is a professor, and if you know that Stuart Russell is a professor at Berkeley, and if you know that UC Berkeley is a university, and most likely you will not pick the basketball player. And also, and one further down, you can get collaborative models. Basically, you go across the documents, right? You have so this happens very often if you have tweets. If you analyze tweets, tweets are very short. The context often sometimes not enough, so you need to go beyond that, and you cross the documents. And also, if you want to separate, depending how you deal with the all dimensions, right? So usually a sentence has multiple multiple mentions, like Washington D.C. and George Washington. So you can do them one by one. You say, hey, Washington D.C. Let's see, is a location, is a person. And then you can handle the other mention as well. So that's the individual method. It's it's a relatively low complexity, but performance is not as good as the next one. Is a joint approach. Then you can jointly determine which one is which. But usually you pay the price, for the higher complexity. So when we talk about machine learning models, a lot of times, we talk about how you generate the features. So traditionally, features are usually generated just from the synthetic features, just the surface form. You look at and also the entity popularity, the type, and the similarity between the entity dimension, and also covariance between all the entities. So deep feature. So if you use a deep learning model, right, deep feature actually is relatively simple. You have word embedding, most likely word embedding, maybe character embedding. Then you have entity embedding, and then you can look at the similarities between the embedding vectors. So here's an example of how people actually use it. Use the deep learning model to do entity disambiguation. So this one actually with the attention. So on the left, these are the contexts. So you have all these context words, and then you go through this this layer. Basically, you're trying to find you're trying to filter them. Basically, because not all the words are useful. Sometimes you just stop words, off, at, and these words are not very useful. You can filter them out with attention mechanism. And also, these are the candidates. All the possible, possible entities like the player, the basketball player, the professor, and the musicians. All these things, and you put them together, and you use them embeddings, and you look at basically this is like an inner product, and you also include the price, the priors, and you train a model on top of that, and that's how you find which one give you the highest score basically. So in this case, so far I'm talking about you do the entity tagging first, and then you do a disambiguation. But a lot of times, if you made a mistake in the first step, you cannot recover. I mean, if I have two examples here, so Romeo and Juliet, right? So by Shakespeare, so you really shouldn't separate them. And the second case, you really should separate them. Otherwise, if you make a mistake here, you cannot find the entrance in the knowledge base anymore. So you could jointly, optimize them. So here is an example. So in the literature, so the New York Times. Basically, you generate lots of you use embedding. Basically, you go up there and you look at the mention, and you do feed forward neural networks. You find a similarity between these part. These are the candidate entities. Then you do another global similarity, and eventually you do a maximum margin loss, and that's how you train the model. So to evaluate, right? So this is similar to tagging actually. So usually you want to find the F1 score, whether you link to the right right entity. Sometimes people use accuracy. That's also I've seen those metrics as well. And if you really want to go back and look at all the papers, sometimes people use like b cubed f1, b cubed plus f1. It's not very common anymore. So if you're interested, you can read the book. I have a reference, but people do not use that very often. So the next one is now we are going to the sentence level. So let's talk about the problem. So in the past, maybe 20 years ago, people talk about intention. The web search intention usually is navigational, informational. So these things basically, if you want to find a place, the Greyhound bus, you want to go to that website. You should go to Google. Maybe the first link will give you that. That's the navigational. And if you want to find information, right, you want to find, hey, San Francisco, how many people there? What's the population? What's the weather? All right. So that's the informational, and also transactional. You go to Amazon, you want to do shopping. That's the transactional. But as time goes, the context has shifted. So we are talking about the conversational AI these days. So
A lot of times it's a task oriented, task specific. For example, if you want to book a flight, so I want to, maybe a couple months ago, I want to book a flight here. So, from FSO to ANC. If you read this, that's the flight booking, intent. And also, if you wanted to know what software to use to view EPUB, that's the software recommendation. So in this tutorial, we focus on the latter, not the web search. So traditionally, people use, this is the classification problem, and these are good friends. They should be your good friends. For example, logic regression, naive Bayes, SVM, and usually people use the features like, this is before the deep learning, right? You use the bag of words, n-gram, TF-IDF, but these days people just use embedding, and on top of that, you build different levels of networks. You can be very simple, very fast, or you can be very complex. You can do bidirectional, and so it really depends on your application. So, for example, you want to have a really fast, classification algorithm. So this is the example, fast text from Facebook. So you can have the bottom layer is nothing but just a word n-gram embeddings. Then you have a hidden layer. The hidden layer actually pretty simple in this case. It's just the average. You take all the things, average them up, and you do a softmax output. So that gives you very fast, but performance action it's reasonable. I mean, it's pretty good. You want to go a little bit deeper. You want to use CNN. So that's doable as well. So in this case, it's each word has an embedding, right? So each column is an embedding vector for the word. Then you have a sliding window. So in this case, this red one actually sliding window of length 2. So you just slide this thing, and every time you slide, you get a value here. This is a vector. Then you have you stack them up. Then of course you need to shrink them as well, because later in the later stage you cannot handle such a big vector. So what we do here is max pooling. So you basically take all these and take a max of all the different components, and you get the maximum pooling. Then then you have different windows. Maybe there's a window size 2, 3, and 4. So then you concatenate them, and then next layer you can do a softmax, and you're trying to figure out what class this belongs to. So you could do a little bit more complex, right? So this one's actually really complex. We just talk about intention. This is a flight booking intention. But a lot of times, if you build a artificial intelligence, bot, for example, if you want to have a chat bot, you say, hey, you type something like, I want to book a flight from LA to Seattle. So immediately the bot will understand that this is you want to book a flight, but that's not enough. You also need to the bot has to figure out, hey, so what are the entities there? What are the slots there? So basically, where is the from? Where is where's the source? What's the source? What's the destination? What the time? Right? You're gonna fly. Usually, these are things we care when we book a flight. So in this particular case, they actually have two components. One is the intention. One is actually you figure out the slot. So I'm not going to talk too much about the slot. That's out of scope for this talk. But just for the intention side, what you do is you have a bidirectional RNN. In the paper, actually, this is the special case of RNN. It's LSTM. You have LSTM. You go from the left to right, and right to left. And you figure out the HIs. So the HI is basically the hidden state of the individual step. And then you do an intention. You do an attention model on that. So this one has attention. It's not showing here, but this intention actually coming from there. So you take the last state. And you take the intention. You predict. Basically this is a softmax here. Then you predict what what the intention is. This. So that was a short, very short introduction to the intention classification. So we're going to talk about the last section in this, in this part, sentiment analysis and opinion miming. So again, we can talk about, what it is, what are the challenges, or traditionally how people do it, and what are the deep learning methods. So in this tutorial, actually, we do not distinguish opinion miming and sentiment analysis. So sometimes there's a minor difference, but in this case, we just think they are the same in this tutorial. So the sentiment analysis mainly study the opinions which express or imply, positive or negative sentiments. So usually, thumbs up, thumbs down, right? So it's pretty simple. I mean, you could have neutral, but just for the simplicity, you just think, it's good or bad. Very simple. So you immediately notice that, hey, this is a classification problem. Indeed, it is. But there's a catch. There's always a catch. So granularity. You can look at document level. You can look at a sentence level, and you can also look at the aspect level. So let me just give you an example what that means. So this just somebody wrote a review at Amazon, for example. So he said 5 sentences. So let's see what he said. So he said, I bought a Canon G12 camera 6 months ago. Okay, so what's the opinion here? Positive, negative, neutral? This is the fact. So not much you can not much sentiment there. And then the second, I simply love it. Summed it up. And third one, picture quality is amazing, and the battery life is long. And however, if you see however, it's going to be go the other side. So if you just look at the whole thing, document level, overall it's a positive review, right? It's positive. But if you look at the sentence level, each sentence, there are some positive sentences. There are, 2, 3, 4 are positive. 5, on the negative side, I would say. And also, if you look at look at the sentence 3, for example, it has more details, not just positive. It says the picture quality is amazing. And also the sentence 4, the battery life is long. So these are specific aspects, and we need actually to figure out all these. Challenges. Okay, so it's not easy actually. Human language is hard to understand a lot of times. So for example, sucks, right? Everybody knows sucks is bad. Indeed, a lot of times it is bad. Then somebody wrote a review and say, hey, this vacuum cleaner really sucks. So I think this probably means it's good, right? Unless you want to buy a vacuum that does not suck. Then sometimes usually people just say, hey, why don't you just pick up all the good words and these are the positive ones, and bad words it's a negative. So sometimes you may encounter this kind of sentence. Can you tell me which camera is good? Okay, you see good, camera is good. So maybe this means that the person likes this camera. But this is the question. We know that this doesn't mean that this is good. It just means this guy is looking for a good camera. So okay, this one is really, really hard. So people usually do not, people usually can figure this out. Machines, very hard. I have a look at, I have read a bunch of papers. Basically, they say, this is a hard problem. So what a great car. So everybody, yeah, this is positive because you have a grade there. But then it says, you stop working in 2 days. So you know what that means. And also, there are cases that, people did not use good or bad, anything, not anything. Just say, this washer used a lot of water. So what does it mean? Do you like it? Do you not like it? Is this a positive, negative? I mean, of course, it depends on your standard. If you want to save water, this is the bad. If you want to, spend water, you want to waste water, this is good, probably. So it's hard to to predict. So traditionally, this basically is a document, classification problem. So there are different ways to do it. Traditionally, again, we look at the different levels, right? There's a document level and the aspect level. For the document level, sentence level, usually it's a little bit simple. A lot of people use a rule-based. So something is great, that's positive, right? Something sucks, most of the time is negative. Of course, we have an exception, over there. A lot of times you have a supervised method. All these classification algorithm, you can use them, and they perform pretty well. So what's difficult actually is the second level. So aspect level sentiment analysis. You not only need to figure out overall the sentence, the good or bad. You actually need to figure out what aspect, where which part the reviewer likes, which part the reviewer does not like, right? For example, in this short sentence, I mean this is just one sentence, but it actually have two. It has two aspects. One is the screen. The screen is clear, but life sucks, right? Life's short. Battery life. So you actually need to extract those. So aspect extraction, usually the people do this two steps. As I just mentioned, you figure out what aspect the people are talking about. This is the screen. The first part is the screen. Second part is battery life. So how do you figure out, what aspect we are talking about? So there's a frequency. Look at the frequent words, frequent nouns, and you look at the opinion and the target. So usually, you look for the the clear, the short, these words, and usually there is a noun before that. So in the case, there's a screen. Usually they are paired, right? You have a screen, you have clear, you have a battery life, you have a short. Sometimes people use a sequential labeling, sequential labeling, sequential tagging algorithm. So basically, you tag them, and also you can use the topic models. So once you figure out, hey, these are the aspects. So tell me, is it positive or negative? So that one actually is slightly easier because it's just a classification problem. The difference between this aspect level and the sentence and document level is you need to limit the scope, right? If you're talking about, if you want to know the screen, good or bad, you do not want to go beyond clear, right? If you go beyond clear, you're looking for short. So if you find that there's a word short, so you actually do not know what the screen is short, what does that mean, right? So that actually does not contribute to this particular sentiment. Deep learning approach, so we usually use our favorite embedding methods, and on the embedding, on top of that, we use CNN, RN. These are standard ways to do it. For aspect-based sentiment analysis, it's a little bit tricky because you do need to extract the aspect first. So you have CNN, there's RN, to extract the aspect. Then you have, once you extract the aspect, actually, you can use attention-based RN memory networks to figure out is it positive or negative. So okay, this is the same example. So I just carry this over. So let me do a few quick examples. So this is a document level. So what the author wants to do actually is usually you have you have a sentence here. Then you're trying to predict the next word. So that's an unsupervised learning method. But the goal is actually not to predict the next word. You already know what the next word is. The goal is actually to figure out the document vector. So you can train this, figure out for this particular document, what is the vector for that. And you get the vector. I mean, our goal is to figure out positive and negative. So you really actually need to take the vector and run a classification algorithm on top of that to figure out whether it is positive or negative. So you can do a little fancy here. So 2 levels, right? So a document usually has more than one sentence, right? A sentence usually has more than one word. So you put all the words together. You do a bidirectional RN, and you do attention mechanism. You figure out the embedding for this sentence, and you put all the sentences together. And you figure out the sentiment for the whole document. So this is actually you go down one level. You say, hey, I just want to just one sentence. So again, this is a CN case. You have words. You have words embedding, and you do. This is similar to the previous intention model. Actually, I think they are just the same technology used in different domains. So I'm not going to talk too much about this. Sorry. So this is how you extract the aspect. So remember, you need to know that what the sentence about is about is about, in this case, I like the food, so this is about the food. Maybe you go to a restaurant, I like the food, but I do not like the service. The waiter, waitress, they sucked. So either how. So you get you get the idea. So this you have to figure out what what is this aspect. So they use the CRF. Basically, it's tagging, right? You need to tag them. This one actually pretty fancy. They actually use the RN. First of all, they use RN, and also they use the dependency parser. So to figure out the different components. So once you figure out what aspect this is about a food, right? This is about a food. So is it positive food or is it negative food? Okay. So I mean, do you like the food or not? So again, you go to embedding and you map to a memory network and you figure out, you do eventually you do a softmax. So that's the basic idea. So I'm gonna skip all these because I think I'm running out of time. So this one, really quick. Again, it's you do sentence level first, then you do all the review. So different sentences, you have a positive. The food is good. Maybe the service is good. In this case, the service is top notch. Top notch is good, right? So these things you can put them together. Another level of LSTM. So that's pretty much. I want to talk about the sentiment. So I'm gonna talk one more section, and we're gonna go to break. Document retrieval and ranking. So I'm going to talk about actually the first part of the candidate retrieval. So for search, mostly search. So mostly search. Sometimes even a recommender system that you want to somebody give a query, or so somebody have an intention. You want to extract the stuff, right? You want to get all the documents. So how do you get them? Usually two different approaches. One is the syntactic retrieval, basically on string match. Right? You're looking for Michael Jordan. So I just find anything that matches Michael Jordan, right? So that actually, if you are familiar with the inverted index, and that's usually how people do it in the real life in a search system. So they are also, since we are at the deep learning age, so we can actually use a little bit more fancier. So for example, you can use a semantic. The problem with the syntactic is, you just match them, match the words, but the words may have different meanings, right? Looking for Michael Jordan, the professor, but you may get a lot of Michael Jordan, the basketball player pages. That's not what you want. So, but semantic can resolve that, can solve that. So let me just introduce the syntactic retrieval. So for example, you want to find the mic. Software engineer. This kind of query happens a lot at LinkedIn. So what happens is you basically you do this offline. You do inverted index. So what documents contain? What documents contain mic? What documents contain software? What documents contain the engineer? And you basically get to the list and you do an intersection. You get the so this one is very simple. Doc2 and Doc4, they have both. They have all the words, so that's it. Now, what's the problem with this? What's the shortcoming? If you have a document that says, Mike is a software developer, for human, right? It's the same thing. I'm a software developer, software engineer, maybe slightly different, but semantically it's the same. You do not get that with this approach. People overcome this by doing query expansion, query rewriting. So basically, you expand that. If you do not do that, you do not get this. So the semantic retrieval actually is conceptually. This particular phrase, this particular query, become embedding some vector. So you pre-compute all the embeddings for different documents. And for this particular query, you basically looking for nearest neighbors, right? So this problem become a nearest neighbor search problem. And this problem has been well studied. You stand here, I'm standing here, I'm looking for my neighbors, right? In a very high dimension, in a very high dimensional space. So the question comes to, hey, how do I generate the vectors? So, you could use a bag of words. I mean, that's that's a traditional method. You can based on accounts, and you can do like a TF-IDF vector. The problem is a very sparse, very large dimension. If your vocabulary is 10K, that's the dimension of the vector. And in that space, you're looking for stuff that's not very easy. So here's a embedding vector comes to help. So word embedding, you can use a different embedding. The pre-trained is you can train yourself. So word to vec, glove, and bird, so on and so forth. You could actually do. I mean, word embedding is if you're just looking for a word. So my software engineer is not a word. It's more than a word. It's a phrase. And you can do like a sentence, a document embedding. So there are different ways to do it. Okay. Okay, I think that's about it. Yeah. So next one will be a ranking. So I think this concludes 2:30. It's about time to take a break. So next, we're gonna take a break. After break, Wei Wei is gonna continue this, and also Huiji and Liang is gonna talk about the real life implementation. Okay, thank you.